All right, guys. Let's go ahead and get into today's warm-up question. And if you're not already there in the warm-up assignment, please make your way there so that you can answer this along with me. And let's go ahead and get our chatter to a minimum so that everybody's focused, because we do have quite a bit of material to talk through today on kind of the basics of circuits. A lot of it should sound familiar because a lot of it is repeating what you saw with that PhET assignment. You do have homework today. You have two different things actually. 1202.1 Circuit Basics Problem Set. It's the first part. Voice. It is the first part of your problem set. And then the second thing that you have for homework is the RA group planning sheet for the electric house project, which hopefully you've already done, but if not, that's why I want to get through this to give you a chance to take a look at one or both of those things. So this is the warm-up question. It shows a picture of a battery, a piece of wire, and a light bulb, and it says, examine the circuit diagram below. Will the bulb pictured in this diagram light up when it's connected as shown? And this is one of the things you were checking in the PhET. You had to put the bulb in different configurations, and then it said, does it turn on? And I saw a thumbs down, so you're saying no? Sam says no. Sam is right. This will not light up. It looks similar to at least one of the ones that you tested. If you don't recall, let me explain why. Perhaps you noticed this, perhaps you didn't. But the light bulb has to be touched on both the bottom and the side. In the PhET, it had a little connection point in both of those places. There were little dashed line circles on the bottom and the side of the bulb. And this is why. That is what the internal wiring of a light bulb looks like. In order for the light bulb to light up, the charges have to have a pathway to flow through the bulb on their closed loop from the battery and then back to it again. And so that has to be part of that loop. And so if you look, in order for that light bulb to light up, the charges have to be able to go in through either the side of the bulb or the bottom of the bulb and then come out through the other position, because this is what the wiring looks like. In order to force the charges through the filament to make the bulb glow, you have to touch it on both the bottom and the side. And if I were you, I would write that down because you might see a question like that again. But you saw it in the PhET. The PhET, you made it even more clear with the little dashed lines. So if you weren't sure why, because we hadn't really talked about it, I think there was a picture like this in there as well. All right. This video clip, I'm actually going to skip past it just because the notes are kind of lengthy. But if you did not watch this, you need to. Natasha. If you did not watch this video, you need to. Okay, this was in the PhET assignment, and it connects last unit on electrostatics with this unit. It has a bunch of vocabulary, but it has history in here as well. And it goes through the different scientists who contributed to our current understanding of electricity and the vocabulary that we use. And it's kind of important when we start talking about conventional current, because that is the model that we use, and yet it is backwards from what's actually happening in the circuit, because at the time when the discoveries were made, the existence of the electron was not known. They didn't know what an electron was. And so they described this movement of electrical fluid, but they talked about an excess of this fluid as being positive, when in reality the fluid, if you will, is electrons, and it's actually a lack of electrons that makes something positive. So everything is labeled backwards. You're going to see that when we look at all of our diagrams as well. They're going to show moving positive charges, and we know from last unit, positive charges aren't the ones that move. And yet it's still the model that we use, at least in this physics class. Now, if you take more advanced physics classes in college and you get into engineering and electrical engineering or anything like that, or just more advanced physics classes, you will learn the electron model for flow, but we're going to talk about conventional current flow. So if you want to know why it's backwards, watch the video. It's in the PhET. It's also in the slides. This is slide 5. Okay. So back to what you saw in the PhET. Circuit requirements. What do you need in order to light a bulb? Okay, this is the requirements of a circuit. You have to have a voltage source and you have to have a closed loop. A voltage source is something like a battery. It's a source of electric potential difference, something that can give a push to your charges to make them move through the wires. The loop is the pathway that the charges take. It's a closed loop, meaning that it can't have any breaks in it, otherwise there's not a pathway back to the battery again. So your closed loop are the wires and the components of your circuit that form a continuous connection from your battery and then back again. And if you have a light bulb as part of this loop, then that light bulb has to be contacted on both the bottom and the side so that the charges can flow through the bulb. That's the only way to get it to light. Again, you saw this in the FET, and we just talked about it a little bit in the warm-up, but these are the requirements for a circuit. Voltage source, which is going to be a battery for us because we're dealing with DC electricity. We're not talking about the stuff flowing through the walls in our houses. That is AC electricity. And then, so voltage source is going to be a battery for us, and then a closed loop. All right, again, if I'm going too fast, you can open this on your own slide. I'm currently on slide 6, if you want to follow on your own screen. All right, now whenever we represent our circuits, we do so with something called a schematic. It's basically a blueprint, a sketch, and it's something you guys have to do for your RA. Part of your RA grade is including schematics that show the components of the circuits that you're going to be building for your electric house project. And so you need to know what symbols to use that represent these different components, and then you need to be able to connect them in a way that's easy to read. Okay, and so here are your symbols. If I were you, I would copy them down so that you recognize how to read a schematic when you have one in front of you, and you know how to draw one for something like your project. The battery, you will see a battery represented by alternating long and short dashes to represent positive and negative terminals. With these dashes, the longer one is the positive terminal, the shorter one is a negative terminal, this battery, and this one has 2 cells because it has 2 sets of short, long. But that's how you represent a battery. A resistor is a zigzag line, and a resistor is going to be a component that resists the flow of charge. It slows your charges down. Typically, we have resistors that serve specific purposes, like a light bulb is a specialized type of resistor, but there's a different symbol for a light bulb. It looks like a circle with a little loop inside to represent the filament of the bulb. Wires are straight lines. A switch, like the light switch on the wall in your house, or a switch on the circuits you're going to be building for your RA, kind of looks like an open door that can be opened and closed because that's what it is. It can close to make the connection or open to break the connection. When we draw the switch in our schematic, we draw it open because if you draw it closed, it just looks like a wire. Okay, so you always draw it so that it is open. The ammeter and voltmeter are tools that we use to measure different variables for your circuit. The ammeter is going to measure current. The voltmeter is going to measure voltage. We'll talk more about each of those. For right now, you just need to know the symbols. A circle with an A inside is for your ammeter. A circle with a V inside is for your voltmeter. But again, those are your circuit symbols. Be able to draw them yourself. Be able to read them and interpret them if you're given a schematic. And again, I'm on slide 8. All right, so if you had a circuit that looked like this, real world, we wouldn't want to draw it like that. That's kind of hard to see. And obviously, the more complicated your circuit gets, the more complicated the drawing is going to appear. So again, we want it to look as simplified as possible. So if you see a battery, you're going to have your battery symbol. When you see a light bulb, there's your light bulb symbol. When you see a switch, there's your switch symbol. If you're trying to draw a schematic, you want all of these components connected by wires. And we try to draw those wires as straight lines at 90-degree angles just to keep everything clean. And so that would be an accurate representation for a schematic for that particular circuit. Okay, so again, be able to draw them. If you want to, you can even add the plus sign on this longer dash for your battery terminal and the minus sign on the shorter dash, just like they are over here. You can add that, you don't have to. All right, so again, that's a schematic. Kind of like a blueprint. You're going to be drawing some, you're going to be reading a lot of them. So circuits can contain the same components, but those components can be connected in different ways. The 2 main types of circuits are called series circuits and parallel circuits, and those are terms that you've already seen because they're in your electric house project information sheet. Here is what those 2 types of circuits look like. A series circuit arranges your components all on the same line so that they're in series one after the other. Like if you were watching a television series, it's one episode after the other, you watch them in order. Okay, and so they look like that all on one loop. A parallel circuit, they are literally parallel to one another on 2 separate loops. So again, those are the main types. We're going to talk more about each one later on. There's a third one that you've also heard of if you looked at your project information sheet. That's a combination circuit, and it actually combines those two together, where you have parts of your circuit in series and parts of your circuit in parallel. We'll talk more about those later on. But again, this is series if they're one after the other like this, and then this is parallel where they're on separate branches. And it literally looks like parallel lines. All right, so again, you can have 2 bulbs and a battery connected in 2 different ways. And that's actually what you're building for your house, so those 2 types right there. All right, I already mentioned that there are a couple of tools that you need to be familiar with. The first is the ammeter. It was represented as a circle with an A inside. You can see it up here in my diagram. An ammeter measures current in series. So if you wanted to know how much current was flowing through the wire, you would connect the ammeter as part of your loop in series. You'll notice that the way that it's connected in this diagram, there is actually a gap in the circuit so that the charges have to flow through the ammeter. It's part of your loop, just like a light bulb, they'd have to flow through it if it was part of your loop. Okay, that's what I mean by it's connected in series. The current flows through it. The ammeter then can read the current. The current is the number of charges that pass by per second, so it's basically counting the charge. Okay, so that's an ammeter. It tells you current, and that's how it's connected. If you saw it on a schematic, that's how you would draw it. It is connected in a different way than a voltmeter. Here's how you would connect a voltmeter. Notice the voltmeter is not part of the loop. The charges don't flow through it. Instead, it's on its own loop. Outside of your circuit, it is connected in parallel. On a diagram, it looks like this, parallel to your circuit on a different branch. If you actually connect the actual device, it looks like this. You're measuring before and after some change in energy. So you'll measure before and after a resistor or a light bulb, or before and after a battery. And then you can see what your voltage is, your change in electric potential across that component. And that's what it says. It measures the change in electric potential of your moving charges, so you connect it outside of the circuit around a resistor or a battery where there's an energy change, and that is your voltmeter. Here's what I mean by energy change. This is an analogy. Obviously, you don't actually lift things up, but it's kind of similar. When I talk about the fact that these charges have electrical energy, this electric potential energy, you can think of it like this, as having gravitational potential energy. The battery lifts them up. It adds electric potential energy to them, or it's analogous to adding gravitational potential energy if it physically lifted them, and now they can go downhill, so to speak. Okay, and so that's what the voltmeter does. It measures places where there's a change in your energy. You'll notice there's a change at the battery. You'll notice the only other change is at the resistor. The battery adds the energy in. The resistor is where the energy is dissipated or leaves the circuit. We'll come back to this idea later on, but that's what is being measured by the voltmeter, is the energy change in those charges before and after one of those components. You can also see that energy change represented in this one because there is a change in color. This has a scale showing maximum energy as red and minimum energy as blue. And when we look at circuits and at the charges moving through them, by the way, this is the conventional current model that I mentioned. If you didn't watch the video, you'll notice these show positive charges. That's not what's really happening, but that's still the model we're going to use. Okay, so you're going to have to get past it. I know it's electrons. That's how we're going to draw it. Okay, everything's backwards. So circuits contain... We're still going to apply these laws of conservation. We've talked about conservation of energy already, which I'll mention in a second as it applies to circuits. In chemistry, you learned about conservation of mass. This is similar. This is called conservation of charge, but it's basically conservation of mass. The same number of charges are in your circuit. Okay, you're not using them up. Those charges don't leave the circuit at the resistor or get created by the battery. It's the same number moving through over and over and over again. Their energy changes, but it's the same number. Circuits contain equal number of particles that flow throughout their loop. Their energy changes, but not their numbers. Conservation of charge. We're not creating or destroying matter. There aren't any more electrons or protons or whatever else. They're just moving through the wire and their energy changes, but we still have conservation of energy principles to apply here. The energy input by the battery equals the energy delivered throughout the loop. The energy that you put into it equals the energy that comes out. Okay, so the battery puts in a certain amount of energy to each of those charges, and those charges dissipate their energy out the resistors along the loop. Okay, so like at a light bulb, you take that electric potential energy and it turns into light energy and heat. Okay, you get this dissipation of energy, but the charges are still there. They still flow through, the battery still charges them back up, and they just keep going around and around. Okay, battery does work in a circuit. It adds energy in, and then you have energy loss at the resistors. Okay, so again, in other words, we still have conservation in circuits. We can look at energy in equals energy out and conservation of energy, or how energy is transferred with the surroundings. Okay, and we also see conservation of charge, where you have the same amount of charge and same amount of mass within your circuit. It's just the energy that is changing. Here's that conventional current model that I was talking about. So this picture shows positive charges moving, but we learned last unit positive charges don't move. The protons stay put. It's the electrons that move. So the conventional current model, although it is incorrect, scientifically speaking, it is still the model that we use because it is the first model that was developed, and instead of relabeling everything backwards, they decided, let's just keep it out of tradition. And so they did. Okay, and so all of our models are going to show positive charges moving. You do need to be aware of the fact that it's actually electrons moving and that everything is actually backwards. So although this circuit shows the charges flowing in a clockwise direction, the actual charges that are moving through are going counterclockwise. But the conventional current model, as long as you're consistent and stick with the same model, you're good. Okay, so it shows moving positive charges. That's called conventional current. We say that our model shows the direction of energy flow from the positive terminal of the battery. We call that the high energy, downhill to the low energy, the negative terminal of the battery. And again, that's what this color change is. We have high energy here. The energy gets dissipated. Now we have low energy, and the battery does work to add energy back into it. Again, please note that it's actually electrons, and they're actually moving in the opposite direction. Here's the direction of your electron flow if you want to sketch it. Charges are present in all parts of the circuit and stay evenly spaced. There is a common misconception among students that the charges are created by the battery. They are not. Electrons and protons and all of those particles make up all matter. Wires are made of matter, the light bulb is made of matter, the battery is made of matter. Everything has protons, neutrons, and electrons in it. And so you're not creating new ones, you're simply moving them. That's what the battery does, it provides the push. And because all of our charges in our conventional current model are all positive, like charges repel, they're all going to stay evenly spaced. You're not going to get a bunch of charge in one spot. Everything stays evenly spaced apart from each other as the charges move through and they flow, quote, downhill, again, for our analogy. The other thing that can be a misconception is this. Because all the charges are moving together, if this was a circuit with multiple light bulbs, all of them would light at the same time. So if there is a question that says which light bulb lights first, it's a trick question. They all light at the same time because all of the charges start moving at the same time. Again, the battery's not making them, so they don't light in order. All the charges move together, and so if you have multiple light bulbs, all of them would light up together as well. Here's another analogy that can help you with the downhill concept. It says by downhill, we mean that charges move from a high electric potential to a low one. Instead of flow of charges, think of flow of water. It's the same idea. If you had a pipe that was level, your water's not going to flow. It's going to sit there. But if you tip your pipe so that one side has higher energy than the other, then you will get a flow downhill, and that's analogous to what's happening in the circuit. The battery lifts up your charges to give them higher energy so that they can then flow downhill. It's an analogy, but if you can understand the concept of water flow downhill, then you can understand the concept of charges flowing downhill from high energy to low energy, which in a circuit is the positive terminal of your battery to the negative terminal of your battery. And again, this is the picture that hopefully helps you to see that same downhill motion. Okay, the battery lifts them up, and then they go downhill from there. Again, the battery doesn't make the charges, it just pushes them. Again, that's a very common misconception. But it pushes them and it gives them the push and they go downhill and then they go back to the battery, they get charged up again and they keep going in this loop until your battery dies, which just means that the reactants in there can no longer do the work to move the charges. All right, so there are some important terms that we need to define, and the first of those is current. So you're going to want to write down current. Current is the flow of electrical charge in a circuit. Specifically, it's the number of charges that pass by per second. That's what I mean by flow. It's your flow rate. Okay, the variable that you'll see for current in our calculations is a capital I, and the unit for current is called the ampere, which I never write out that whole thing. I write out amps. So you'll see the current in this circuit is 1 amp, okay, or 0.5 amps. You could abbreviate that further with just a capital A. So if you see just a capital A, that's amps. Just like instead of writing out meters, you can just do a lowercase m, same thing. Okay, the current in a circuit is measured with a tool called an ammeter. Now you can see where it got its name. An ammeter measures amps, which is current. Okay, so again, current is the flow of electrical charge. It's the number of charges per second. It is measured in amps with an ammeter. Factors that affect current. So how many charges pass by per second is going to be determined by the voltage of your battery. If you have a battery with a large electric potential difference, a lot of push, then you're going to have a faster flow of charge and a higher current, a higher charge rate. The other thing that affects your current is resistance, which we'll define in a second, but it was defined in the FET as well. Resistance is determined by these factors. So we're going to come back to these. You've seen them before, they were in the FET. But the length of your wire or conductor, the width of your wire or conductor, how thick it is, the material that it is made from, the temperature of it, and the number of pathways. All of those things affect the amount of resistance, which in turn affects the amount of current. Okay, we're going to go back to the same table. You'll recognize it in a minute. If you did the FET, you'll see the same table we saw in there. And again, if you're trying to copy this and I go too fast, this is slide 21. All right, so I told you we're going to define resistance. Here you go. Resistance, this is the next really important term for you to write down. So far we have current and resistance. Resistance is a measure of the opposition to current flow in a circuit. They are exactly opposite. If you have a lot of resistance, it means that you have a small amount of current because it's resistance to flow. Okay, it's measured in a unit called ohms, which you can write out the word ohms, or you can use the Greek letter capital omega, which is what that is in that this parentheses right here. This is the symbol. Again, that hindrance to flow, the resistance, is due to collisions. The reason that the charges flow more slowly is if they're colliding a lot. So if you ask yourself what would make these charges collide, then in your mind you need to think those are the things that make more resistance because they're causing collisions, and collisions make the charges slower. Anything that increases collisions increases resistance, and thus means that you have less current, less flow in your circuit. This is the table I said that hopefully you would recognize because you saw it in your FET. If you didn't write it down then, you should write it down now. These are 4 of the factors. The 5th one was the number of pathways, but these are 4 of the factors. The length of your wire, you're going to have less resistance if it's shorter. Think about collisions. If you have charges that only have to flow a short distance, there are going to be fewer collisions. The longer they have to travel, the more likely they are to continue colliding. The second thing is cross-sectional area, which is another way of saying thickness. You can tell those have very different thicknesses. Again, think of it like you walking down a hallway with 20 people. If you are charges, you and those 20 other people, and you're in a big hallway, you're less likely to run into people than if you're in a very narrow space, you're going to run into more people. Okay, and so that's more collisions, and for charges, that's more resistance. So the greater your cross-sectional area, the thicker your wire, the less resistance you have because there are fewer collisions. The thinner your wire, the more resistance you have. The material affects it as well. I'll give you a list in a second, but copper, for example, has less resistance than iron. It's just a property of that material. Temperature. Again, you know this from chemistry, hopefully, but the hotter a material gets, the faster its particles move, and faster movement means more collisions. So the hotter it is, the more collisions you have, more resistance, less current. And the opposite is also true. All right, so let's focus on that material just for a second. It's one of those 4 factors. Here's a list of materials with their conductivities. You don't need to memorize the list, but I do want you to know that silver is the most conductive metal. So if you're trying to purchase a wire, a charging cable, and you want it to be the most efficient, silver wire is best. Followed by copper, it's second. Followed by gold, and then aluminum. Don't buy a wire made out of anything else. It's a waste of money. Okay, those are going to be the ones that are most conductive. Now, silver, even though it's the best conductor, they don't use it as much because it's more expensive, which is why copper wiring is so common, because copper is a less expensive material, but its conductivity is still really good. I wouldn't buy gold. It's not as good as silver or copper, and it's more expensive than both. And then aluminum. Aluminum is the cheapest option, but it's also, out of those 4, the least conductive, but it's still a really good conductor. It's still better than all of your other metals. So just know those 4. If you want to memorize them in order, that would be helpful. All right, silver, copper, gold, aluminum. Ohm's law is the equation that relates current, resistance, and voltage to one another. The equation is V equals I times R, or if you look at the formula chart that we have in class, it is written on here as I equals V over R. It's the same thing. If you rearrange it, you get I equals V over R. If you want to write it the same way it is on here, I would write it that way. I equals V over R, or you can write it this way, V equals I times R. In that formula, that delta V, or V, is voltage. I'll tell you right now, this doesn't have the delta in front of it. Even though voltage is change in electric potential, this just says V. So that's your voltage. The I is your current, and the R is your resistance. So this formula will allow you to calculate one of them if you know the other 2. We're going to do some practice problems with it in a minute. You don't need to write down that sentence down there. That is just the equation written out in sentence form. It says the electric potential difference, or voltage, between 2 points on a circuit is equal to the product of the current and the total resistance. Again, that's what the equation says. You don't need to write it down. But you do want the equation, V equals I times R. Let's practice using it. This one says, what current flows through a hairdryer plugged into a 120 volt circuit if it has a resistance of 25 ohms? Again, label things. My equation I already know, V equals I times R. My V is 120, my R is 25, plug them in. Okay, so I have 120 equals I times 25. If I want to solve for I, which is my current, I need to get it by itself, divide both sides by 25. That's what goes in your calculator. 120 divided by 25 gives me a current of 4.8. But guys, don't leave it like that. I'm missing my unit. What should my unit be for current? Check your notes. It is amps. You can just write it as an A if you want. If you want to write the word amps, you can, but A is how I'm going to write it. 4.8 amps. Again, guys, this math should be pretty easy. It's only a 3-variable equation. All right, let's try another one. Find the resistance of a light bulb when connected to a 6-volt battery if the current is 0.3 amps. Again, plug the numbers in where they go. Label them first if you need to. My voltage is 6. My current is 0.3. I'm looking for R. Divide both sides by 0.3, and I have R equals 6 divided by 0.3, which gives me a resistance of 20. And again, I want my unit. My resistance unit is ohms. That's that capital omega, that Greek letter. Funny looking one. Okay, so that's how you're going to write that. Follow-up question. If the bulb is swapped with one that has 2 times the resistance, what will the new current be? Well, this resistance is 20 ohms. If it's 2 times as much, it would be 40 ohms. You can recalculate it, or you can recognize the proportional reasoning stuff. Let's go ahead and do the recalculation first. If I swap it, again, it's still the same battery, still 6 volts, but now I have 40 ohms instead. What will the new current be? Plug it back in and solve for I, which will be 6 divided by 40, or 0.15 amps. Guys, that's half as much current. It was 0.3, now it's 0.15. That makes sense. Twice the resistance will be half the current. They're inversely proportional to one another. We saw it with the definitions. Okay, resistance and current are inversely proportional because they're defined as the opposite of each other. Current is flow of charge and resistance is hindrance to flow. So if you have twice as much hindrance, you're going to have half as much flow. Bless you. All right. Again, whatever you need to write down there about that relationship, or you can copy down that particular example. By the way, what changes to a bulb could result in more resistance? We have a whole list. Okay, more resistance is going to come from a longer wire. So if you had a longer wire in your bulb, that would do it. If you had a thinner filament, a thinner wire in your bulb, that would do it. If you changed the material to something like tungsten instead of copper, that would do it. Okay, there are all these factors. You can look back at the list, but all of those things that would increase resistance could be an example of something that you could change in a light bulb to get more resistance. The other equation you need to know is power. Now power, the only formula on your formula chart is this first one. Those other two that are in this box, not on your equation sheet. You can memorize them if you want, or you can solve for them by substituting Ohm's law into the power equation, or just take 2 steps to do your math. Okay, either way. But the first one is the only one on here. The first one says power equals voltage times current. That's on your formula chart. Electrical power is the rate at which electrical energy is supplied to a circuit or consumed by a load, and it has the same unit as mechanical power from last semester, watts. Okay, so power is still measured in watts, but now we're talking about electrical power instead of mechanical. Let's do an example calculation. This one says, calculate the resistance of a toaster oven if its power is 800 watts when it's connected to a 110 volt outlet. The problem with this, you'll notice, is that my power equation doesn't have resistance in it. So you have to take 2 steps. We're going to use the power equation to solve for current, and once we find current, then we can go to Ohm's law and we can solve for resistance. Or you can memorize one of those other 2 equations that were on my previous slide. But I'm going to do it in 2 steps so I don't have to memorize anything. My power, 800, equals 110. My voltage times I. Solve for I. Divide both sides by 110, and I is 7.27 amps. Now that you know the current, you can go back to your other equation for Ohm's law. You can plug it in along with your voltage, and you can find resistance. So plugging in looks like this. 110 equals 7.27 R. Divide both sides by 7.27. And your resistance is 15.1 ohms. So you will see 2-step problems, but they're both 3 variable equations, so it should be pretty straightforward. Are there any questions about this example? All right. That's it for today's notes then. For the rest of the period, you now have time to work on 1202.1. You guys have 18 minutes, so you've got enough time to actually finish that entire assignment because it's pretty quick. You can use your time to work on that, or if you prefer, the other thing that's due today is your electric house planning sheet. If you haven't finished that, do that first because you need your group in order to do that. And guys, we start building on Monday. You need materials on Monday. If you don't have them, you will be behind and you may not have enough time to finish it in class. Okay, so start figuring out who's bringing what. Get each other's phone numbers or make a group chat or whatever. Remind each other over the weekend you need stuff on Monday. All right, go ahead and get to work. If you have questions for me, please let me know.